All right, welcome back, Master Technicians. Today we are diving into an advanced explainer covering something you're seeing every single day now, mini-split DC-Inverter Compressors. Look, if you've been out in the field lately, you already know these systems are totally taking over the market. But diagnosing them? Yeah, that takes a completely different level of understanding compared to the old traditional setups we all cut our teeth on. So today, we're going to break down the complex inner workings of these units into clear, actionable steps that you can actually use on the job. And hey, this comprehensive technical breakdown is brought to you directly by Level Up HVAC Training. We designed this material specifically for you, technicians who are ready to elevate their diagnostic game. Everything we're talking about today is built on real-world service data pulled right from Carrier and Lennox systems. We're giving you the precise numbers and the exact methods you need to confidently troubleshoot in the field. Okay, here's our game plan for this session. 1. Inverter theory and power flow. 2. Boards and components. 3. Diagnostics, tools, and testing. And finally, 4. Sensors and system protection. Let's get right into it. Section 1. Inverter theory and power flow. We're talking about converting and switching. You know, to truly appreciate what an inverter does, we really have to compare it to the old school stuff we're used to. Think about it. Old fixed-speed models, they're basically blunt instruments. They lock in at roughly 3,600 RPM, they try to regulate the room temp by slamming fully on and off, and they absolutely hammer the power grid with massive inrush amps every single time they start. But inverters? They are a completely different beast. They soft start incredibly smoothly, and then they ramp their speed up or down to match the exact cooling or heating load of that specific room. They run continuously at lower hertz, which gives you those whisper-quiet, super stable temperatures, and honestly, it yields a massive 20 to 40% energy savings. It's a real game changer. So, how exactly do they pull this off? Well, the magic really happens through a 3-step power conversion process. Step 1. The unit takes standard single-phase residential AC power from the wall and runs it through a bridge rectifier to convert it into raw DC power. Step 2. The DC bus capacitors and the PFC reactor smooth out and boost that raw power into a highly stable, high-voltage DC bus. For a typical 230-volt unit, we're talking about 310 volts DC. Finally, step 3, the Intelligent Power Module, or IPM, uses IGBT switches to basically chop that DC bus up, synthesizing it right into a 3-phase AC output for the compressor. 1 phase in, 3 phase out. Pretty cool, right? Let's trace that actual power flow so you can visualize it. Over on the left side, you've got your basic single-phase 60 Hz wall power coming in. You can follow that path right through the rectification stage, into the energy storage of the DC bus, through the big boost of the PFC reactor, and finally into that inversion stage. That's where the IGBT module steps in, acting kind of like a high-speed traffic cop, routing power perfectly to the U, V, and W terminals of that 3-phase compressor motor. Now, the absolute crucial takeaway here is all about frequency, which we measure in hertz. The rate at which those IGBTs are switching open and closed, that equals your hertz. And this is exactly what the main board is constantly varying to set the compressor speed. So a lower hertz means lower synthesized AC voltage, which gives you a slower pump. A higher hertz, that means higher synthesized AC voltage, a much faster pump, and a whole lot more heating or cooling capacity. The inverter is literally out there making its own custom sine wave. All right, moving to section 2, boards and essential components. Let's look at the actual physical powertrain. When you look at the actual inverter powertrain board, you can map out that exact theory we just talked about directly onto the hardware. Over on the left, there's your bridge rectifier. Just above that, those massive copper coils, that's your power factor correcting PFC reactor. And dominating the top center are those huge cylindrical DC bus capacitors. Keep in mind, those caps are actively storing that highly stable 310 volts DC. It's so vital for you to be able to recognize these physical components because honestly, when a board fails, doing a quick visual inspection right here is very often your very first clue. Now let's zoom in on how this builds into the final stage of that powertrain. See this heavy-duty component bolted directly to the heatsink? That is the Intelligent Power Module, or the IPM. This is what actually houses those IGBTs. These switches use a fascinating process called pulse width modulation, PWM for short, and they fire in very precise pairs. By rapidly alternating the power through the U, V, and W terminals from both the positive and the negative sides of that DC bus, this little module builds that beautifully controlled sine wave that physically drives the compressor. But here's the thing. The IPM doesn't think for itself. The real brains of the entire operation sit over on the main control board.
This board relies heavily on its EEPROM memory chip, which holds the specific, custom programming for that exact model of unit you're working on. It gathers up all the environmental data from the thermistors and the pressure sensors, calculates the actual room demand, and then commands the target speed in hertz straight down to the IPM. It's basically the conductor of the whole orchestra.
Which brings us to Section 3, Diagnostics, Tools, and Testing. How do we actually troubleshoot this flow? First things first, guys, you absolutely cannot diagnose these highly sensitive systems blindly using old standard tools. You absolutely 100% need a true RMS multimeter to accurately read those synthesized hertz and AC volts. You also need it to check resistance and perform your diode checks. Alongside that, you'll need a reliable clamp meter to verify your running amps against the unit's nameplate. And here's a pro tip. You need skinny back probe leads. I'm telling you, trying to jam a standard fat test probe into those incredibly tight UVW terminals is a guaranteed way to short out a very expensive board and ruin your whole day. So before you touch a single terminal, we need to talk safety. These are not the simple 24-volt contactors we used to deal with. You must power off the unit completely at the disconnect. But listen, you are not safe yet. Those giant DC bus capacitors we looked at, they can hold a lethal 310-volt charge long after the power is cut. You must put on high-voltage insulated gloves and safety glasses, and you absolutely must safely bleed down those capacitors. Whatever you do, do not short them out with a screwdriver. Well, unless you want to permanently weld it to the casing. Use a proper discharge resistor, usually something around 100 ohms and 40 watts, to safely bleed that voltage all the way down to zero. Okay, once you have positively verified with your true RMS meter that the DC bus is completely dead, then, and only then, can you safely move on to measuring the compressor motor windings. This step is where you determine if the heavy lifting machinery of the compressor is still intact or if it's actually the root source of your whole system failure. So here is your step-by-step diagnostic process for that. Step 1. Physically disconnect the 3 compressor leads from the board, so you are totally isolating the motor. Step 2, measure the resistance between U to V, then V to W, and finally U to W. On a 3-phase inverter compressor, all 3 of these readings must be nearly equal. Step 3, if any of those legs read open line, or OL, you've got an open winding. If it reads a dead short of 0.00 ohms between the windings, the compressor has failed. And finally, step 4, check each winding directly to the copper ground of the unit. It should read OL, meaning there is 0 continuity. If your meter beeps to ground, that compressor is grounded out and it needs replacing. No way around it. All right, our final stop. Section 4, Sensors and System Protection. Let's look at the system's fail-safe loop. A lot of techs get really stuck here, so I highly recommend you just memorize these exact thresholds. For Carrier and similar systems running R410A refrigerant, a high-pressure switch trips at a massive 639 psi, which is going to throw a P1 fault code, and it will not reset until that pressure drops all the way back down to 464 psi. On the flip side, the low-pressure switch is generally looking for a loss of charge, right? It trips at a dangerously low 20 psi, throwing a P2 code, and it resets at 43 psi. Memorizing these exact parameters takes all the guesswork out of reading your gauges.
Now, if you suspect you've got a bad switch, physically disconnect its plug from the board to test its resistance. A healthy, fully closed switch in a normally pressurized system should read exactly 0 ohms. Just for some context, the static system pressure of an R410A unit just sitting there idle should be right around 188 psi, which is well within the safe, happy zones of those switches. And remember, the board doesn't just use these sensors for hard emergency shutdowns. It's actively monitoring that pressure and the thermistor data to proactively limit the compressor's hertz frequency. For example, if the discharge line starts getting way too hot, the board will automatically slow the compressor down to prevent catastrophic damage way before a trip even occurs. It's protecting itself.
Well, as we wrap up this Level Up HVAC training explainer, I want to leave you with a really crucial mindset shift. As a master technician, when you open up a condenser out in the field and you find a burned-out inverter board, you always have to ask yourself, did this board die of natural causes, like a random power surge, or did a failing component murder it? Think about it. A shorted compressor winding or a grounded motor will instantly kill a brand new, expensive board the very second you power it up. Always do your checks, test your hertz, verify your voltages, and ohm meter your windings before you just start swapping parts. Thanks so much for learning with us today, guys, and keep leveling up those diagnostic skills. Catch you next time.